Welcome to another deep dive, everyone. Today we're going to be exploring conservation laws.
Yeah. And it's a concept that I think you'll find is, all around us.
Yeah.
It might even change how you see the world.
Okay, well, I'm ready to have my mind blown. So let's start with the basics.
Right.
What exactly is a conservation law?
Mm.
I have to admit, when I hear that phrase, I immediately think about like protecting the environment or, endangered species.
Right.
But I have a feeling we're talking about something a little bit more abstract than that.
Yeah, a little bit. I mean, you're on the right track with the idea of protection or like preserving something.
Okay.
Um, Essentially, a conservation law it's a statement that says a particular measurable property of an isolated physical system doesn't change as the system evolves over time.
Okay, so it's like something is staying constant even though things are changing within the system.
Exactly.
Yeah,
Exactly.
yeah.
It's like, think of like a bathtub filled with water. You've got water flowing in from the faucet and then water draining out, maybe some evaporation happening.
Right,
But, if we carefully track all those inputs and outputs,
right.
the total amount of water in the bathtub
Yeah.
is going to stay the same over time.
Okay, I see. So we're basically accounting for all the ways water enters and leaves the bathtub.
Right.
But what about the water that evaporates? I mean, it's still water,
That's a great point.
just in a different form.
Yeah, yeah. And it highlights the importance of defining what we're actually trying to conserve.
Okay,
So in this case, we're talking about the conservation of mass.
okay.
The total mass of water in the system stays constant, even though it might change state from liquid to vapor.
Right, okay, so it can change form, but the total amount of matter involved stays the same.
Exactly.
Got it. Okay, so how do we express this idea mathematically?
So we can use a pretty simple equation to represent this. And it basically says this. Accumulation equals what goes in minus what goes out, plus what's generated inside minus what's consumed inside.
Oh, wow. Okay, well, that sounds a little bit intimidating, but I think I get the general idea.
Yeah.
Like we're basically just tracking all the different ways a quantity can change within a defined system.
Exactly.
And you mentioned system earlier.
Right.
Is that important?
Yeah, absolutely. To apply these laws, we need to define a control volume.
Okay.
Think of it like an imaginary boundary
Okay.
that encompasses the system that we're interested in.
Okay.
So in our bathtub example, the bathtub itself is our control volume.
Right.
And we're only really concerned with the water inside that boundary.
So we're basically setting the limits of what we're observing and measuring.
Exactly.
I'm starting to see how this could get pretty complex when we start applying this to more dynamic systems.
Yeah, you got it.
Yeah.
And the beauty of conservation laws is that they can be applied to a vast range of different phenomena. I mean, from the motion of planets to the flow of traffic, to the growth of populations.
Populations. Okay, now that's intriguing.
Yeah,
I'm picturing a bustling city with people coming and going,
right. Exactly.
new babies being born, and sadly, some folks passing away.
Right. So we can use that same principle of conservation to model population dynamics.
Okay.
Let's take a simpler example, though. Imagine a population of bacteria
Okay.
growing in a petri dish,
Okay.
and they reproduce at a certain rate,
Uh-huh.
but they're also being preyed upon by some microscopic predator.
Okay, so it's like a tiny little unseen battle for survival happening right there.
Right, exactly.
So how do we factor in those kind of opposing forces of growth and predation?
So we can use a mathematical tool called a differential equation to represent these rates of change.
Okay.
Now, before you get intimidated by the term differential equation, let me assure you, it's not as scary as it sounds.
Okay, I appreciate that. All right, so give me the simplified version.
Right.
What does a differential equation actually tell us?
It basically describes how a quantity changes over time,
Okay.
taking into account factors that either increase it or decrease it.
Got it.
So in our bacteria example,
Yeah.
it helps us understand how the population size fluctuates due to that interplay.
Right, between reproduction
Exactly.
and predation.
Exactly.
Okay, yeah, so if the bacteria reproduce faster than they're being eaten, then the population grows.
Right.
And if the predators are more efficient, then the population shrinks.
Right. And what's fascinating is we can actually use this model to predict how that population will change over time
Oh, wow.
under different conditions.
Wow, that's pretty amazing.
And we can even manipulate the system to achieve a desired outcome.
Okay, so like if we wanted to control the bacterial population,
Right.
we could adjust the predation rate by maybe introducing more predators
Right.
or finding ways to limit their food supply.
Exactly. You got it. And This principle has far-reaching implications. I mean, understanding population dynamics is crucial for things like managing ecosystems, controlling disease outbreaks, even predicting the spread of invasive species.
Wow. I never realized that something as seemingly simple as like counting bacteria could have such profound implications.
Right. That's just the beginning.
Yeah.
These conservation laws, they're like a universal language that help us make sense of the world around us, from the tiniest organisms to the grandest cosmic events.
That's incredible.
Yeah.
Wow, I'm certain to see these conservation laws everywhere.
Right.
Like it's like this secret code underlying the operations of the universe.
Yeah.
But tell me, do these laws only apply to like physical things like water or bacteria or populations,
Right.
or can they be applied to more abstract concepts too?
Yeah. That's a great question. And it leads us to an even deeper understanding of these principles.
Okay.
So while we often associate conservation laws with, tangible quantities,
Right.
the underlying concept can actually be extended to more abstract realms as well.
Okay. I need an example.
Okay.
My brain is still stuck on bathtubs and bacteria.
Sure. Consider the concept of information.
Okay.
In many ways, information behaves like a conserved quantity.
Okay.
It can be created, transmitted, stored, and even seemingly destroyed.
Right.
But the total amount of information in a closed system remains constant.
So, like when I try to whisper a secret to my friend across a crowded room,
Mm-hmm.
and the message might get distorted along the way,
Right.
but the original information still exists somewhere,
Exactly.
even if it's like garbled and mixed with other sounds.
Right. Think of the classic game of telephone. The
Mhm.
message might change a little bit
Yeah.
as it's passed along,
Right.
but the original information,
It's still out there somewhere.
exactly.
Okay.
And this principle has significant implications for things like computer science, cryptography, even our understanding of how knowledge evolves over time.
So even in the digital age where it feels like information is constantly being created and shared, we're still bound by this fundamental law of conservation.
Exactly.
Right.
It really highlights the interconnectedness of information
Okay.
and the limits of what we can truly create or destroy.
Right.
But it also raises intriguing questions about the nature of knowledge itself.
Okay.
So if information is conserved,
Yeah.
does that mean that knowledge is also conserved in some way?
That's a mind-boggling thought.
Right.
So are we essentially just swimming in a vast ocean of information?
Yeah.
Constantly like exchanging and transforming it,
Right.
but never truly adding to or subtracting from the total amount.
It's a fascinating concept to ponder.
It is.
And it speaks to the enduring power of ideas
Right.
and how they persist and evolve over time, even as they're passed from one person to another.
Right. Yeah. Speaking of passing things along, we've talked about how this conservation law applies to like fluids or populations or even information.
Right.
But I have a feeling there are even more applications out there just waiting to be discovered.
Absolutely. Think about the human body, for example.
Oh.
Our bodies are incredible examples of these complex systems
Right.
that rely on a delicate balance of inputs and outputs.
Okay, so how do conservation laws play a role in like keeping us alive and functioning?
So, for starters, consider the law of conservation of energy.
Okay.
So, this law dictates that the energy that we take in through food
Right.
must be balanced by the energy we expend through activity and metabolic processes.
So if we eat more calories than we burn,
Yeah,
that excess energy has to go somewhere.
Yes,
right?
yeah.
It gets stored as fat.
exactly. And if we consistently consume fewer calories than we need,
Yeah.
our bodies start breaking down stored energy reserves
Gotcha.
to make up the difference.
Okay, it's all about maintaining that balance.
Right.
Okay, this is making me rethink my whole approach to nutrition. It's not just about what we eat. It's about understanding like the energy flow within our bodies.
And that's just one example.
Right.
Our bodies are constantly regulating things like temperature, fluid balance, all kinds of other variables just to maintain this stable internal environment.
It's a remarkable feat of biological engineering.
It really is.
It's amazing to think that the same principles that govern the motion of planets also influence like the flow of blood in our veins.
Yeah, it really is a beautifully interconnected universe.
Yeah.
Speaking of the universe, let's zoom out for a moment
Okay.
and consider, some of the grandest scales imaginable.
Right.
So conservation laws play a crucial role in our understanding of cosmology
Okay.
and the evolution of the universe itself.
Okay, now you've really piqued my curiosity.
Hmm.
How do these laws apply to something as vast and mysterious as the universe?
Well, for example, the law of conservation of energy
Yeah.
tells us that the total energy of the universe
Right.
remains constant, even as it expands and changes over billions of years,
Right.
which has profound implications for our understanding of the Big Bang
Wow.
and the ultimate fate of the
So
universe.
even though stars are born and galaxies collide, the total amount of energy in the universe stays the same?
Yes.
That's mind-blowing.
It is. It speaks to this profound interconnectedness of everything in the cosmos. We're all just part of this grand cosmic dance,
Yeah.
governed by these fundamental laws of physics.
This is definitely one of those aha moments I was hoping for.
Right.
I'm starting to see the world in a whole new light, appreciating the intricate balance and interplay of forces
Right.
at every scale.
Yeah. And it's not just about appreciating the beauty of it all.
Right.
These laws have very practical implications as well.
Okay.
You know, by understanding these principles, we can develop new technologies,
Okay.
make informed decisions,
Right.
even solve some of the most pressing challenges facing humanity.
That's what I find so exciting about this conversation.
Yeah.
We're not just exploring like abstract concepts,
Right.
but we're also uncovering the tools we need to make a difference in the world.
Exactly. These laws provide a framework for understanding and influencing our surroundings,
Right.
whether we're talking about managing ecosystems,
Right.
designing sustainable energy systems,
Huh.
or even making wise financial decisions.
Oh, speaking of finances,
Yeah.
it makes me wonder if we can apply these same principles to something as seemingly mundane as managing our money.
You bet. In fact, one of the most relatable applications of conservation laws can be found in the world of personal finance.
Okay.
Let's consider a scenario we're probably all familiar with.
All right.
Taking out a loan to buy a house.
The great American dream, often accompanied by a mountain of paperwork and interest payments.
Right.
So how does this conservation law factor in?
Well, think about it.
Okay.
You borrow a certain amount of money.
Right, the principle.
The principal, exactly.
Yeah.
And then you have to pay it back over time plus interest.
Right.
That sounds a lot like our bacterial population, right?
Okay, yeah, I see the analogy.
Yeah.
The principle is like the initial population.
Mhm.
The interest is like the growth rate. And our payments are like the predation, trying to bring that balance down.
You got it. And just like with the bacteria, we can use a mathematical model
Okay.
to represent this loan repayment process.
Right.
In this case, it's a differential equation
Okay.
that describes how the loan balance changes over time
Okay.
based on the interest rate and the amount you pay each month.
So we can use this equation to figure out how much that dream house will really cost us in the long run.
Exactly.
Okay.
Factoring in all those pesky interest payments.
Wow. This is starting to feel like we've unlocked a secret code that applies to everything,
I know.
from microscopic organisms to our own personal finances.
Mhm.
It's both empowering and a bit overwhelming.
And that's the beauty of these conservation laws is,
Yeah.
they offer this powerful framework for understanding these seemingly disparate phenomena
Yeah.
in a unified way.
Uh-huh.
It's like having this universal key that unlocks insights in countless fields.
So even though the applications seem vastly different, at their core, they all rely on this same fundamental principle.
Precisely. And what's truly remarkable is the power of mathematical models
Yeah.
to describe these real-world processes,
Uh-huh.
no matter how complex they might appear.
This is truly eye-opening. It's like seeing the world through a new lens, appreciating the intricate connections and the underlying principles that govern everything around us.
And this is just the beginning.
Wow.
The more we explore these laws,
Yeah.
the more we realize how deeply they're woven into the fabric of reality.
Yeah.
They challenge our assumptions, they spark our curiosity, and they lead us to profound new insights about the universe and our place within it.
This whole conversation has really shifted my perspective. It's like I've gained this new appreciation for the intricate workings of the universe, from the smallest bacteria to the grandest cosmic events. It's all connected in ways I just never imagined.
And that interconnectedness is truly awe-inspiring. The same principles that govern the motion of planets also influence the flow of blood in our veins, the transfer of energy in ecosystems, the growth of economies. It's a beautiful tapestry of cause and effect.
So, okay, I have to ask, if we can use these conservation laws to understand and even manipulate systems, does that mean we can like predict the future? Like, can we use these equations to know exactly what will happen in a given situation?
That's a question that has philosophers and scientists debating for centuries. While these models give us, powerful tools for prediction, there are always limits to our knowledge.
So you're saying there's always an element of uncertainty.
Exactly. We can never account for every variable, every unforeseen event, every random fluctuation. The universe is a complex and dynamic place, and there's always room for surprise.
So even with all our scientific advancements and our amazing equations, we'll never be able to create a perfect crystal ball.
Perhaps not a perfect one, but that's what makes life so intriguing, right? There's always something new to learn, something unexpected around the corner.
I have to admit, this deep dive has left me feeling both humbled and exhilarated. Humbled by the vastness and complexity of the universe, but also exhilarated by the power of human curiosity and our drive to understand it all.
And that's the beauty of it. The more we learn, the more we realize how much more there is to explore.
Well, on that note, I think it's time to wrap up this deep dive, but before we go, I want to leave our listeners with a final thought to ponder.
Okay, I like this. What's the challenge for our fellow knowledge seekers today?
So we've talked about how energy and mass can convert into each other, as per Einstein's famous equation. Ili Poswad, does this challenge our traditional understanding of conservation laws? Or does it simply expand our definition of what's being conserved? It's something to mull over as you go about your day, noticing the conservation laws at play all around you.
What a fantastic way to tie everything together. It's been a pleasure diving into these fascinating concepts with you. Until next time, keep those minds curious and those questions coming.
And as always, thanks for joining us on The Deep Dive.